All right, well, welcome back after the lunch break. Our next speaker is Namrata from the University of Birmingham. The floor is yours.
Thank you, Santa, for inviting me to the LMS. So today I am going to be talking about intersecting set systems and Hamiltonicity. This is a joint work with Arturo Merino and my then PhD supervisor, Sosten Mutse. So I think some of you might have heard this talk in bits and pieces before, but hopefully it's new for many of you. So let me start by introducing Kneser graph. So the topic said, the title said intersecting set system, but I want to start with the Kneser graph. So these are actually one of the graphs at the forefront of intersecting set system and the most actively studied graph. So let me start by defining what these are. So there are two parameters, small n and small k. The vertices are the k element subsets of set 1 to n, and there is an edge between two sets if they are disjoint. So this is one example of a Kneser graph, the complete graph. So here you see k is 1. So all these vertices are actually the singleton set and they are disjoint. So we put an edge between every pair of vertices and we get a complete graph. Another very popular example is the Petersen graph. In this case, n is 5 and k is 2. So as you can see, the vertices are the two element sets of set 1 to 5. And we put an edge between two sets and only if they are disjoint. So throughout the talk, we will assume that k is at least 1 and n is at least 2k plus 1. Otherwise, you will just get a very trivial graph on two vertices. So let me start you by telling a bit of origin story of these graphs. So in 1955, Kneser gave a conjecture. This is actually a set theoretical conjecture. So imagine that you have some k subsets of n sets and you want to divide such sets into multiple classes. So in the class, you keep on adding all these sets until they are not disjoint. Okay. So he conjectured that if you have so many k subsets of n set and if you want to put it into n minus 2k plus 1 classes, there will be at least then there'll be at least one class where you have two disjoint subsets in the same class. And you can change that set theoretic language in a graph theoretic language also. So Lovash exactly did that in 1978. He then introduced these Kneser graphs where he put those k subsets as the vertices of a graph and you put an edge between two vertices when the sets are disjoint. So those classes will then correspond to the number of colors you would need to properly color the Kneser graph. And he proved that the chromatic number of such a graph is n minus 2k plus 2. So see, you need one extra class if you want to properly color it. Yeah. And this was a very much celebrated result in combinatorics because he used some nice results from topology to prove this theorem. And that actually started a field of topological combinatorics on its own. These graphs are also vertex transitive, meaning, informally speaking, the graph looks the same from the point of every vertex. And for these vertex transitive graphs, Lovash already had a conjecture from generality that he said every connected vertex transitive graph admits a Hamilton cycle. And there are just 5 known exceptions so far. This conjecture is still wide open. So we will not try to tackle this one in the talk. So we'll only work with the special cases of the conjecture, which is the Kneser graph. That's also vertex transitive. And one of the 5 exceptions is actually a Petersen graph, which I showed you in the first slide, where n is 5 and k is 2. So Petersen graph has a Hamilton path, but it does not have a Hamilton cycle. Okay, so I just want to revise few of the known results about these, about the Hamiltonicity in the dense Kneser graph. So broadly speaking, Kneser graph can be divided into 2 categories, dense and sparse. So graph is dense when n is large with respect to k. Okay, so I will just write some of the known results. So you can see that these graphs have been under study from the 70s. So Henrich and Wallace in 1978, he proved that when n is at least that quantity, the corresponding graph will be Hamiltonian. And there was a series of improvements over the years, and that the result in the blue, that is the best known result for the dense case, where n is at least 1 plus log of 1 times 2.62k. The graph is Hamiltonian. Now let's look at the Hamiltonicity of graphs from the other direction, that is from the sparse. The sparsest case is when n equals 2k plus 1. Because n has to be at least 2k plus 1 to be a non-trivial Kneser graph. So that would be the sparsest case. So just for that sparse case itself, there were conjectures from 3 different people in the 70s that said that the graph, such a graph is also called odd graph. So Kneser graph when n equals 2k plus 1, that is also known as odd graph, just a different name. And they conjectured that it admits a Hamilton cycle, again with that exception, Petersen graph. And then in 2021, it was proven that odd graphs indeed are Hamiltonian. And using a conditional result from Johnson in 2011, they also extended this result to the cases when n equals 2k plus 2 raised to a, when a for all a at least 0. So see, when a equals 1, for cases when n equals 2k plus 2, the graph is Hamiltonian. So this is the best known result from the sparse direction. So combining the results from the last 2 slides, we see that when n lies between these 2 quantities from 2k plus 3 to 1 plus log 1 times 2.62k, when n is not equal to this quantity, we do not know whether the graphs are Hamiltonian or not. So this is the problem we will be tackling in this talk. And so that gives our first result. All the Kneser graphs, with the exception of the Petersen graph, is actually Hamiltonian. Recently, this result was also accepted at Advances in Mathematics journal. So, and with this result, we settle the Hamiltonicity of all Kneser graphs in full generality. Now, I also want to talk about some other classes of graphs, intersecting graphs, which are defined by intersecting set systems and also related to Kneser graphs. So this one is called generalized Johnson graphs. It has 3 parameters, n, k, and s. The vertices are the same as Kneser graph, and edges are the pair of sets A, B, such that the size of intersection is exactly s. So as you can see, when s equals 0, what we get is the original Kneser graph. And when the size of intersection is k minus 1, so exactly 1 less than k, we get the ordinary Johnson graphs. These graphs are also vertex transitive. Again, I want to talk about third category of classes of graphs, which are again related to Kneser graphs and also defined by intersecting set systems. These are called Schrijver graphs and stable Kneser graphs. The Schrijver graph has 2 parameters, n and k. So this is the vertices here are a bit different from the Kneser graphs. So vertices are again of size k element subsets of 1 to n. But we have to make sure that in the set there shouldn't be 2 adjacent elements. So for example, if k is 2, n is whatever, you cannot have a set with elements 1, 2, because 1 and 2 is adjacent. And this is cyclically, so you cannot even have n and 1 in the set. And the edges are like Kneser graphs. We join 2 sets only when they are disjoint. And a slight generalization of Schrijver graph is called S-stable Kneser graphs. So n, k, and s, it has 3 parameters. So in the case of Schrijver graph, we saw that elements shouldn't be adjacent to each other. But here you add some more generalization that says that the 2 elements should be at least distance s apart. And the edges, we connect the edges when the corresponding sets are disjoint. Okay, so these were all the different graph classes I looked into this intersecting set system. So I'll just give you some more results. So J and K, which was the generalized Kneser graphs, they are also Hamiltonian for all k at least 1 and k at least 2k plus 1 without unless n, k, and s are these 3 triplets, which is just your normal Petersen graph. And for Schrijver graph also, it has Hamiltonian cycle for all these correct values of n, k, and s. Okay. So, I mean, you can always have a very contrived notion of intersecting graph, which is defined on intersecting set systems. But these three classes of graphs were kind of very natural to me. So that's why I'm writing this statement that it settles the Hamiltonicity problem for graphs which are defined by intersecting set systems. Okay, so this was all theory so far. Now I want to talk about the proof outline. So now we saw three results, but the proof I will give you only for the Kneser graph because that is the start of the entire proof. Because once you have the Hamiltonicity proven for Kneser graphs, coming up with the proof for Schrijver graph, stable Kneser graph, generalized Johnson graphs are not, I mean, I wouldn't say very trivial, but not comparatively a lot easier than Kneser graph. So let's see the proof. So we saw that for the sparsest case when n equals 2k plus 1 and n equals 2k plus 2 was already settled before this result. Yeah, so these are the previous papers that settled these cases. So our new case will assume that n is at least 2k plus 3. So this means that even with our new result, the old two results are not obsolete. One would still need them if you want to claim that all Kneser graphs are Hamiltonian. So it works in two steps. So first one is to construct a cycle factor. Cycle factor means collection of disjoint cycles. And this step actually works for all n at least 2k plus 1. So for this step one, we are fine. So once you have these collection of cycles, we want one big cycle, which is a Hamiltonian cycle, right? So we need to glue those cycles together. And for that step, we need this assumption that n is at least 2k plus 3. Okay, so for step number 2, we need one would need to depend upon the previous proofs, and it would not work for cases when n is not is less than 2k plus 3. Okay, so once you have these cycles, we would need to understand the properties, what would help in joining those cycles together. So that we will see in the later slides. And the later slide we will also see that when the properties of those cycles will remind you of a game called Conway's Game of Life. So it's actually a zero-player game, and you have some entity called a glider, and all you need to tell the glider is its initial configuration, and there are some set of rules of the game. So once you have defined the initial configuration of the glider, it will just keep moving on its own based on the rules that you have provided. So hopefully you will. I mean, if you know this game, the slides will remind you of somewhat of it. Okay, so let's see how the step one, how can we create cycle factor? So remember, cycle factor was the collection of cycles. So I'm coming to the another representation of the vertices of the Kneser graph. So we saw it was a set of size k, but now I want to represent the set as a binary string. So it's a different representation. So for example, in this case, when n equals 11, let's say k is 4, and x is your set, let's say 4, 7, 8, and 10. So I want to define a binary string x. Okay, so it's a binary string, and the length is n. So the length of this string is 11. And we want to put 1 at positions 4, 7, 8, and 10. And for all the rest of the positions, it will be 0. So in this picture, I have marked 1 with dark boxes and zeros with the light box. Okay, so once we have these ones and zeros, we represent 1 by the opening parenthesis and 0 by closing parenthesis. Okay, and what we do is we do the cyclical parenthesis matching. We just match the ones and zeros together, the closest pairs of ones and zeros. So for example, this 1 and 0 will be matched. 1 and zeros are matched. This 1 and 0, and as I said, it's a cyclical matching, so this one with the first 0. Okay. So now you have, with this process, you have the set of bits in the bit string. Some are matched and some are not matched. So what we do next is the ones which are matched, the zeros and ones which are matched, we complement those matched bits. And let's assume that's a function f. Okay. So when you apply function f, the matched zeros will become 1, and the matched ones will become 0, And whichever were the unmatched zeros before, they will remain as is at the position. So look carefully for this x and fx. So if you try to convert this x and fx back to its set format, so you can see that there is in these two strings, ones are not at the same position. So if you convert this x and fx back to sets, those sets will be disjoint. Because ones are not at the same position, because you are deliberately complemented ones to zeros. So that would mean that x and fx is an edge in a Kneser graphs because x and fx are disjoint. So if you keep on applying this function f to, let's say if you have x to fx, then f squared x, f to f cube x, all those things. So you would, this f is invertible actually, and it will give you a cycle. You will eventually go back to reach the first vertex. Okay, so I mean, we got one cycle, but that is not a Hamiltonian cycle. Otherwise, this problem would be extremely simple. So what actually it does is if you apply this function f to all the vertices of the Kneser graph, you will get disjoint cycles. Okay, so then that is the definition of a cycle factor. Okay. So at the end of this step, what we have so far is just some collection of disjoint cycles, not the Hamiltonian cycle so far as of now. Okay, so I have an example just to make things super clear. So this is a Kneser graph when n equals 6 and k is 2. So the vertices are the two element sets. Okay, and I have put an edge between two sets when they are disjoint. Okay, so let's start with that bit vector 1, 1, 0, 0, 0, 0, which means set 1, 2 in the graph. So let's apply function f. So when we apply it, we'll see that will be the new vertex. Okay, so one will move 2 positions right. Okay. And I have highlighted the corresponding edge in the graph. Okay. So the second vertex is 3, 4. So there is an edge between 1, 2 and 3, 4, and that edge is in red in the picture. If we apply function f again, and that will take us to 5, 6. And when you apply it again, you come back to 1, 2. So after application of f so many times, you get cycle of length 3. So but see, this is just a triangle. There are still a lot of vertices which are not covered yet by this cycle. So we take any of the vertex which has not been covered yet. Okay, let's say that vertex 1, 3. And it's the same thing, you keep on applying function f. Function f means, again, remember, you match the closest pair of ones and zeros and complement it. That is what function f is. So in this case, we get a cycle of length 6. Again, some of the vertices are not covered by both these two cycles, so we continue the process. So we have a yellow cycle of length 3, and then green cycle of length 3 again. So with all these 4 cycles, we see that all the vertices are covered now. So these are your cycle factors. So we see that in this cycle, there are 4 cycles: the red one, orange one, green one, and blue one. And the next step is obviously to combine them together into one cycle. And so this was the step 1, the easiest step. Okay, so before we think about joining the cycles together, we have to understand its properties. Okay, because that would only help us to join the cycles together into a nicer way. Okay, so let's do some analysis. We'll start with a very simple graph. K is 1, so there is just one in the vertex. So these are the vertices of the Kneser graph, and this is a cycle of length 15 because K is just 1 here. Okay. So as you can see, with repeated application of function f, this black dot keeps moving towards the right. But this is a static picture. I want to interpret this as some dynamic kind of thing. Okay. So I want to define an entity that moves over the time. Okay. I want to give this a dynamic picture. Okay, so here it is. So it's the same cycle, but now we have matched zeros, ones, and zeros. Okay, so this one is actually matched one is represented by the dark red box, and its corresponding matched zero is the lighter red box. Okay.
Are you missing should that be enough a block shaded?
Sorry?
So that's column 4th one.
Oh yeah, you're right. Yeah, that's right. There is no Like, oh, so you mean the fourth row from the bottom?
Yeah,
Yeah. You're right. There should be a match 0 there. That's true. Yeah. So, as I said, I want to give this a picture of dynamic system. So, I have to come up with an entity, and this entity we also call a glider, which is what we have copied from the Conway's game. So, we say that these two matched bits, 1 and 0, they form one glider. Okay. And this repeated application of f, so that one application of f we count as one time step. So what we can say that there is a moving entity called glider, and in this picture it moves by 1 unit every time step. Okay. So this was a super simple Kneser graph. Let's go to a slightly complicated graph. In this case also, again, n is 15k is 2. And these matched ones are actually together. It could be far apart also, but in this example, it's 1, 1, they are together. And as again, when you put colors on these black and white boxes, the two dark red ones will be matched ones, and corresponding to lighter reds are the corresponding matched zeros. So in this case, we say that these 4 matched bits actually forms a glider. Okay, and in this case, the glider actually moves by 2 units per time step. So glider is nothing but a set of matched ones and zeros. And as I said, I'm repeatedly saying that we want to see it as a dynamic system. So we have come up with a quantity called speed of the glider. So in this case, the speed of the glider will be the number of ones or the number of zeros because they are the same. So, okay, so in the first picture, left-hand side, the speed of the glider is 1. And the second picture, the speed of the glider is 2. So as I said, those were the super simple Kneser graphs. But here also it's simple only. But in this case, we have 2 different kinds of gliders. Gliders with speed 1 and the speed 2. Yeah. So after one time step, the red glider will move 1 step ahead. The glider will move 2 steps ahead. So we want to study these movements of glider more formally. Okay, so we define something called the position of the glider after certain time step. Okay, so S0 this is just the formula of the uniform motion we took from the physics. So S0 is the initial position. We have V, which is the speed of the cycle, and T will be the number of times you have applied function. As you can imagine, these are the very nicely separated gliders. So after for a long time, they will move at the uniform speed. The red glider will keep moving at speed 1, and the blue glider will keep moving at speed 2. But as you can imagine that these gliders could be interleaved in a super complicated way. So the motion cannot be always uniform. Okay. So for this short talk, it's very difficult to describe what would happen in a non-uniform motion. But what I can say is there will be some time steps where the glider didn't move at all. Okay, so it remains stuck at the same position. And some of the gliders, they move faster than their usual speed. Okay, so that is what I mean by non-uniform motion. Okay, so now we come at the most important part, which is called glider partitioning. So here in this case, let's say this is some vertex of a Kneser graph where n is 18 and k is 7. So we did this nice parenthesis matching where we matched the closest pairs of ones and zeros, and we came up with these black and white boxes. Okay, but at this point, it's not very clear that so I said match bits forms a glider, but it is not very clear at this point which of these match bits will be a part of which glider. Okay. Yeah. So see, this is my glider partition, the second one. This has been done with using some complicated recursion, again, which is out of the scope of this talk. So as you can see, the first 3 black boxes, I colored it with red. Okay, this next 0 is again light red. Okay, so far so good. But the next 0 and 1, they are green in color. And the next one is red. Next one is blue. And then we see these 2 remaining red boxes that has to be matched with the first 3 dark red boxes. Okay, so it's not if I just give you this above picture, it's very difficult to, you can come up with lots of different configuration of gliders. Okay, you can match, but it has to be defined in a certain way. And that is what we call assigning a bits to gliders. That is called glider partitioning, and that part is actually complicated. So there is an internal recursion which is going on here, which actually assigns the match bits to gliders. Okay. But yeah, for now, you assume that there is a process that can assign the bits to the gliders in a nicer way. Okay, so why we took so much effort to introduce this dynamic quantity called glider? Why can't we just be happy with the static picture of matched zeros and ones? Because once we have this quantity called glider, we can find some nice invariants for a cycle. Okay. So for example, in this above picture, the colored picture, we have, if you see the speed set of the gliders which are in that picture. So the red has speed 3, the green and blue have speed 1 each, and the pink one has speed 2. Okay, so then in this case, the set of speed is 3, 2, 1, 1. Okay. So if you keep on continuously applying this function f on that glider, or on that vertex, if you keep on applying function f, you will have one cycle, right? So what I am claiming is that for each of the vertices in that cycle, if you count the speed set of gliders for each of those vertices, they're all the same. It might look different, obviously it will look different, but the speed sets will be same in all the vertices of one single cycle in a cycle factor. And that's why we say the speed set of gliders is a cycle invariant, and that property will actually be very useful coming up. But also I want to say that there could be many cycles with the same glider set. Okay, so this doesn't characterize a cycle. Unfortunately, we do not have a cycle characterization. So there is no such list of properties that is unique for a cycle. But for proving this our theorem, this result is enough for us. We do not really need to understand super deeply what's going on in the cycle. Just the fact that the speed set of glider is invariant, that's enough for us. Okay, so now we are towards the last step of the proof. So so far we saw how to come up with different cycles in a cycle factor using a parenthesis matching approach. We learned that the gliders in each of the speed set of gliders in each cycle is an invariant. Okay, so we will now, the last step of the proof is to join the cycles together. Okay. So let's assume there are two cycles in the cycle factor C1 and C2. Okay, and so for in this example, it's just the length 6 cycle just for the simplicity. So you have vertex x in C1. So the next, if you apply function f, you will get to the endpoint of the edge x fx. And for C2, let's consider some vertex y. Okay, so again, if you apply function f, the next vertex will be fy. So you have this structure. Right. So now we want to understand, we want to find a nicer pair of x and y. Nice means, so we want to come up with x and y in such a way such that x and fy, if you look at x and fy, the sets corresponding to x and fy, they should also be disjoint. Then only you can have edge like x fx. Okay? And similarly, we want a situation when the sets corresponding to fx and y, they should also be disjoint. Then only you can have such a crossing edge, fx and y. Okay, so you have to come up with such xy such that x, fy, y, and fy is actually a 4 cycle. Okay, so once you have such a 4 cycle, you can get rid of the edges on the cycle C1 and C2 and use those crossing edge. Okay, so once you do this, you will be able to join the cycles together. And similarly, or if you have some collection of cycles, all you need to for each pair of cycles, all you need is such 4 going cycles, and then you are done. Basically, you will be able to join all the cycles together in the of the cycle factor, and we will get a Hamiltonian cycle. But there are some subtleties here. So first one is that these joining, it's called growing cycle, those four length cycles, they must be disjoint. That's the first condition. So for example, if you have this red cycle C1 and C2, that's fine. C1 and C2 will be joined together as one. But the edge that you have used on C2, it shouldn't be repeated again to join any other cycle. So if you draw a picture where you have used that red edge on C2 to join these two cycles C1 and C3, you will see that it's not actually, you are not able to traverse all the vertices of these three cycles. Okay? It won't be a Hamiltonian cycle. The first condition is that flowing cycles must be edge disjoint. Okay, so now, so imagine us now, before I get into this, imagine a situation that you have these cycles in a cycle factor, right? So imagine a big auxiliary graph. So all these cycles are considered as the vertices of such a big graph, okay? And we put an edge between those two cycles if we have such a pair X and Y, okay, for that big auxiliary graph, right? So if we prove that such a graph is connected, that means it would have a spanning tree. Okay. And if it has a spanning tree, that means all the vertices, which means cycles, are actually traversed. And that would give us a Hamiltonian cycle in the original graph. So that's the whole idea. We need to prove that that auxiliary graph is connected. So there is a pair of X and Y. There's a nice pair of X and Y between the cycles. So basically, if it is connected, that means there is a path from one cycle to every other cycle. But how we will make sure of that? How we can prove that such a graph is connected? Okay, so we need to join the cycles together, but we have to do it in a very controlled way to make sure that we get a spanning tree. Okay, so we join the cycles such that the speed of gliders increases lexicographically. So remember this property of the glider that I mentioned earlier, that the speed set of glider is actually a cycle invariant. Okay. So for C, we can represent C1 just by giving the speed set of gliders which are present in the vertices of cycle C1. So, and we write down that as a non-increasing format. Okay. So let's assume for C1, their gliders are 4, 3, 3, 2. Okay. So we join it to the another cycle such that the speed set of, if you consider this as a number partition, there's a lexicographic increase in the speed form. So for example, 4332 and 4431. 4431 is bigger than 4332 lexicographically. Okay, so we try to join these two cycles together. So let's see. In this case, we have 4332, right? Which means K here is 4 plus 3 plus 3 plus 2, which is 12. Okay. So there will be a cycle in this cycle factor, okay, whose glider set is just the singleton set 12. Okay. It's not shown here, but there will be such a cycle. Okay. So let's say you start with cycle C1. You start finding these pairs X and Y. Okay. So you keep joining, you keep going to the cycles with increasing glider set lexicographically. So eventually you will end up with a cycle whose glider set is 12, 12, 0, let's say 12. Okay, so you start with cycle with glider set 1, 1, 1, 1, 1, all 1, and then you eventually go to the cycle with glider set 12, 0. Okay, so that's the cycle with the which has the largest speed set of gliders considered lexicographically, and that would so in this case we have increased the speed of the slowest glider by -1 and increased the speed of the one of the larger gliders by 1. So the glider set increases lexicographically, and this will ensure that such a big auxiliary graph that I spoke about, that graph is actually connected, which would imply that it has a spanning tree, and that would imply that original graph is Hamiltonian. This was the rough sketch of the proof. Okay. Right. So now we are moving towards the last slide, where we talk about some open questions. So the first question is about efficient algorithms. Okay, so this graph, the proof that we gave is actually a constructive proof. So it's very easy to come up with a straightforward algorithm but that algorithm actually runs in the size of the Kneser graph, okay, which is exponential in terms of n and k, small n and small k, because the number of vertices are exponential in n and k. But for these kind of things, we want an efficient algorithm, and efficiency is defined in a different way here. So let's say I tell you that, okay, this graph is Hamiltonian cycle, and I give you one vertex on that cycle. How much time will you take to give me the next vertex of the cycle? Okay, so for that time, we want it to be polynomial in small n and small k. But as of now, that would also, I mean, as of now, we do not know that. You have to construct the entire graph, entire Hamiltonian graph. Then only you can, if I give you the entire graph, anybody can tell me what is the next vertex. So, so here efficiency is polynomial in terms of small n, small k, in terms of generating the next vertex of the Hamiltonian graph. Okay. Thank you, sorry. So for Kneser graph, we do not know this, but we have a slightly good news when it comes to Schrijver graphs. So in Schrijver graph, we prove that they are, and both stable Kneser graph also. So in those two classes, we prove that they are Hamiltonian, and we also have a nice efficient algorithm in terms of small n and small k for those two graph classes. Okay, so as you remember the original conjecture by Lovash, that where he said every connected vertex transitive graph, apart from those 5 exceptions, they are Hamiltonian. So in this talk, we only deal with one class of such vertex transitive graph. So there are lots of different families of Cayley graphs which are also vertex transitive, but we do not yet know whether they are Hamiltonian or not. Okay. And so the first step of Hamiltonicity is always to prove that the graph is Hamiltonian. And once you know that, these are the next steps usually people do. So they want to understand whether the graph is Hamiltonian connected, which means for every pair of vertex in a graph, there is a Hamiltonian path. Yeah? And the second research area could be Hamiltonian decomposition. Okay, where we need to find for a graph, we need to find edge disjoint Hamiltonian cycles. Okay, so for Kneser graph, we do not even know whether there are two edge disjoint Hamiltonian cycles. So proving even that result first would be a big deal. Yeah, so that's all about it. Thank you. Yeah.
So you said you don't know if there are two edges joined, but you know that there are two different ones. So do you know anything about low bound on the count of Hamilton cycles?
You're asking the lower bound on the count of the number of edge disjoint Hamiltonian cycles?
Not edges, just not distinct.
No, okay, no, for Kneser graph, we do not know the lower bound, but for the odd graphs where n equals 2k plus 1, there is a lower bound. I think it's double exponential.
So does your algorithm improve, your result, does it improve the trivial bound on finding a Hamiltonian cycle in Kneser graph? I mean, do you shave off anything?
The trivial bound on?
Well, just brute forcing, right? You could always do exponential algorithm and brute forcing.
Unfortunately, no. Yeah, I mean, that's why we need, the proof is constructive, but we really have to find a nice efficient algorithm. As of now, you have to construct the whole thing, then that's the only algorithm. Yeah, but I think it's better than brute force at least, because if we have these cycle factors and a nice way to find these XY pairs, okay, so it is still exponential in terms of it is polynomial in terms of the size of the cycle. But I think it's for the brute force is exponential in terms of the size of the cycle, right? So I think that's better. Yeah.
No questions? Is there any online questions?
Yeah.
Yeah, someone is raising.
So we do have one more. We do have one question from online. I'll unmute Mano again.
Oh no, I just wrote my comment. I really enjoyed the talk, and I think the theorem is really deep. And it was sort of funny for me also to hear that you quote your theorem coming from some conference, and then you say, oh, by the way, it also appeared in Advances of Mathematics, which is the most prestigious journal. So I kind of had a moment of smiling at differences in cultures between computer scientists and mathematicians. Anyway, no, I just had a comment which I wrote. I didn't mean to speak, but now I have. Thank you.
Thank you so much for your lovely comments.
All right, two more questions. More questions? No, let's thank the speaker again then.